We tend to think of dinosaurs as the ultimate rulers of Earth, but what if I told you giant insects reigned before them? In the Carboniferous period, oxygen levels soared, creating a bizarre world of dragonflies the size of eagles. How did this peculiar period come to an end? Earth as we know it began as a chaotic, fiery world, roughly 4.54 billion years ago. Born from the swirling dust and gas that surrounded the young sun, it took shape through gravity pulling fragments together. These fragments smashed into one another, generating immense heat, leaving Earth a molten sphere under constant bombardment by asteroids and comets. Its surface was a red-hot volcanic expanse, while the air above was non-existent, no oceans, no clouds, just a searing, unstable crust, surrounded by the vacuum of space. Among the most dramatic events from this period was the Moon's creation. Scientists believe an object the size of Mars, dubbed Theia, collided with the early Earth. The impact was so powerful it flung debris into orbit, which later coalesced into the Moon, locking it into its familiar role as Earth's silent partner. This collision likely also tilted Earth's axis, shaping the planet's seasons even in its earliest days. This dramatic time is known as the Hadean Eon, a fitting name derived from the Greek word Hades to describe a hellish environment. During this period, Earth began to cool just enough for its interior to differentiate. The heaviest materials, like iron, sank inward to form a dense core, while lighter silicates rose to create the mantle and the planet's first thin, fragile crust. This internal layering would be fundamental to the planet's future, providing the dynamic geology that defines Earth today. Water, essential for life, may not have been native to Earth. One leading idea suggests it arrived through extraterrestrial deliveries. Icy comets and hydrous minerals within asteroids that pummeled the planet during its early years could have carried water molecules. Over time, these bombardments added enough to eventually form the first oceans, although that future was still millions of years away. Despite endless destruction, Earth was already developing its first defensive system, its magnetic field. Generated by the movement of molten iron within the core, this invisible shield offered vital protection from the sun's harsh solar winds, which could strip the atmosphere away. Without it, the planet might never have stabilized enough for life to emerge. However, in many ways, the surface of early Earth resembled an otherworldly vision. For millions of years, its entire exterior may have been covered by a glowing magma ocean. Rivers of lava cascaded across the surface, glowing brighter than the fire under the scorched skies. The atmosphere, if it could be called that, would have been filled with gases from volcanic eruptions, carbon dioxide, water vapor, methane, though completely devoid of the oxygen that sustains life today. But time was already changing the planet with surprising speed. The Earth's young crust expanded and fractured under internal pressures. Volcanic islands began to emerge from the molten seas, tentative hints at the tectonic activity that would later define continents and seabeds. Meanwhile, its vast rotation kept the planet spinning frenetically. Days were only 6 hours long, a pace nearly unimaginable now. Even in this hostile environment, the seeds of habitability were planted. Elements crucial to life, carbon, hydrogen, nitrogen, were likely scattered across the planet by the asteroids and comets that rained down relentlessly. Each fiery impact was, paradoxically, setting the groundwork for the complex biological processes that would appear billions of years later. This volatile beginning wasn't just a story of destruction and chaos, it was a transformation. Earth was shaping itself into a distinctive world, laying the foundation for its oceans, atmosphere, and habitable surface. This violent chapter in its history may seem unimaginable to us now, but it was the very chaos of these early years that made life possible. Life on Earth likely began nearly 4 billion years ago, just as the planet was cooling from its tumultuous formation. With the presence of liquid water, a key ingredient for life, conditions were finally right for something extraordinary to happen. Yet, instead of complex organisms or plants, the very first life forms were far simpler. Single-celled organisms, known as prokaryotes, these microscopic pioneers thrived in extreme environments where modern life could barely survive. Deep beneath the ocean's surface, hydrothermal vents released a cocktail of chemicals into the water, creating prime real estate for these early microbes. Unlike plants or animals, they didn't rely on sunlight for energy. Instead, they used a process called chemosynthesis, breaking down compounds like hydrogen sulfide to extract energy. This ability to survive without sunlight allowed them to colonize some of the most inhospitable spots on the planet. Near scalding volcanic fissures or within acidic pools, these microbes carved out ecological niches where few others could thrive. For billions of years, these organisms were Earth's sole inhabitants. They thrived quietly, yet they began to change their environment in profound ways. Some of the earliest intact evidence of their existence comes in the form of stromatolites, layered rock formations created by colonies of microbes as they trapped and bound sediments. These structures still exist today in a few rare places, like Shark Bay in Australia. Gazing at a modern stromatolite is like looking billions of years into the past, to when these tiny architects dominated Earth's surface. Scientists often talk about LUCA, the last universal common ancestor, as the starting point for all life on Earth. LUCA is not a single fossilized creature, but a theoretical microbe whose genetics link every living thing on the planet. It may have lived around 4 billion years ago, leaving behind no physical remains but a molecular blueprint that echoes in the DNA of every cell. Studying LUCA helps researchers reconstruct the web of life and understand the evolutionary pathways that began so early in Earth's history. One of the most astonishing aspects of these ancient microbes is their resilience. Some of them could survive in environments completely alien to us, such as without oxygen, light, or even organic nutrients. Their robust nature has led some scientists to hypothesize that similar life forms could survive on other worlds, like Mars or Europa, where extreme conditions mirror early Earth. The adaptability of these organisms underscores just how hardy and flexible life can be. Though simple in structure, microbes ruled Earth for an unimaginably long time. More than 80% of Earth's history belonged to them alone. To put that into perspective, if Earth's 4.5 billion year history were condensed into a single 24-hour day, microbes would dominate for nearly 20 hours. Humans, by contrast, would only appear within the last few seconds before midnight, a mere whisper in Earth's story. Microbial life was quietly laying the groundwork for everything that followed, even if it might not have looked like much at the surface. These organisms were processing chemicals, interacting with the environment, and slowly beginning to transform the planet in ways that would drive the next stages in evolution. They set the stage not just for more complex life, but for the entire history of biology itself. Over billions of years, these tiny architects made Earth habitable for everything that came after. Around 2.4 billion years ago, a tiny group of life forms made a change that would echo across Earth's history. Cyanobacteria, simple microbes living in ancient seas, developed the ability to harness sunlight and perform photosynthesis. This biochemical trick allowed them to convert water and carbon dioxide into energy while releasing oxygen as a byproduct. At first, this oxygen was absorbed by the oceans and reacted with dissolved minerals, but over time, the excess began to escape into the atmosphere. The Great Oxidation Event, or GOE, had begun, and it would completely alter the trajectory of life on our planet. Before this time, Earth's atmosphere lacked oxygen entirely and was instead dominated by gases like methane and carbon dioxide. The introduction of oxygen was a revolutionary step, but not everyone benefited. For much of Earth's microbial life, oxygen was toxic. These anaerobic organisms, accustomed to a world without any trace of oxygen, were driven to extinction or forced into isolated, oxygen-free pockets of the planet. What was initially a triumph for some microbes acted as a global catastrophe for countless others. The Great Oxidation Event wasn't just a chemical transformation, it was Earth's first mass extinction. But the changes brought about by oxygen didn't just affect life. Oxygen's interaction with methane, a greenhouse gas that helps trap heat, led to a dramatic cooling of the planet. With methane concentrations falling, Earth's temperatures plummeted. These conditions triggered what scientists believe were the first global ice ages. During these snowball Earth episodes, glaciers may have covered the planet from pole to equator. Even the oceans froze over, creating a reflective layer of ice that limited sunlight from reaching the surface. For millions of years, Earth became an icy wasteland, its blue-green seas hidden beneath a blanket of white. Eventually, volcanic activity began tipping the scales back toward warmth. Erupting volcanoes released massive amounts of carbon dioxide, a powerful greenhouse gas, into the atmosphere. Over time, these emissions created enough of a warming effect to melt the ice sheets and end the glacial period. As the ice receded and oceans thawed, Earth emerged from the frozen state, setting the stage for more complex life to evolve. The fluctuating climate during this time likely played a key role in driving the development of new survival strategies among the planet's simple organisms. Beyond transforming the planet's climate, the oxygen-rich atmosphere created by the GOE allowed for another breakthrough: the formation of the ozone layer. Oxygen in the upper atmosphere began converting into ozone molecules, which were uniquely effective at absorbing harmful ultraviolet UV radiation from the sun. For the first time, life forms could begin venturing closer to the surface without the constant threat of lethal radiation. The cyanobacteria responsible for the GOE had prepared Earth for a future where life could thrive in shallow waters and eventually on land. Evidence of this transformation can still be found today. Layers of ancient rust-colored rock, called banded iron formations, are direct evidence of the oxygen introduced by microbes. When oxygen first began accumulating, it reacted with iron in the oceans, creating these deposits. In a way, this oxygen-driven process created Earth's first pollution event, with rusting iron painting a vivid picture of ancient oceans that were beginning to change forever. For millions of years, Earth teetered between being a frozen snowball and a warming greenhouse, driven by the chemical domino effects set off by tiny photosynthetic microbes. While these changes seemed sudden in Earth's history, they unfolded over unimaginable timescales, completely reshaping the planet Cyanobacteria, the unassuming architects of this transformation, had unlocked the potential of a new atmosphere, one that would one day support complex forms of life, including us. This so-called oxygen revolution was a slow but monumental step in transforming Earth from a hostile world into the cradle of biology. Around 635 million years ago, Earth emerged from a deep freeze, a planet-wide ice age that had encased much of it in glaciers. What followed was the Ediacaran period, a quiet yet monumental chapter in life's history. It was during this time that the first large multicellular organisms appeared, a dramatic shift from the microscopic single-cell dominance that had defined billions of years. These creatures were the pioneers of a new biological order, and yet they were unlike anything we'd recognize as animals today. Ediacaran organisms were soft-bodied and strange. Some looked like fronds, gently swaying on the seafloor, while others took the form of rounded discs or quilted pillow-like structures. Without mouths, eyes, or digestive systems, they absorbed nutrients directly from their surroundings, possibly through their skin or by filtering particles in the water. They thrived in shallow seas, sprawled across the ancient ocean beds, living in ecosystems that were still simple and low energy. There were no predators, no competition for survival as we know it today. Life was in its earliest stages of experimenting with complexity, testing out different body plans and functions in a world very different from the one we inhabit. By this time, oxygen levels were high enough to support multicellular life. While oxygen played a role in their evolution, it was still nowhere near the levels needed to sustain the more dynamic ecosystems that would come later. The Ediacaran was a time of steady, deliberate progress, rather than rapid evolutionary leaps. Organisms remained sedentary or slow-moving, tied to the seafloor and dependent on the delicate balance of their environment. The fossil record from this period gives us remarkable, if rare, glimpses into this ancient world. These fossils, often preserved as imprints in ancient marine sediments, have survived thanks to extraordinary conditions. Without the hard shells or bones that came later in evolution, the delicate bodies of these organisms typically decayed quickly after death. This makes preserved Ediacaran fossils incredibly valuable and, in some cases, puzzling for scientists. Some of the best-known specimens, like Dickinsonia, featured flat-ribbed bodies that could stretch over a meter long, giants considering life had been microscopic just one period earlier. Yet their place on the tree of life remains a mystery. Were they early animals or an entirely separate branch of life that vanished without descendants? A fascinating feature of Ediacaran organisms is their uniqueness. Many of them have no known modern relatives. While some researchers interpret this as evidence of early evolutionary experiments with form and function, it raises the possibility that entire branches of life emerged and disappeared during this period without leaving any genetic legacy. What we're left with are isolated blueprints of biology that seem alien in their design, biological whispers from a world long gone. Interestingly, the Ediacaran biota, as these creatures are collectively called, wasn't formally recognized in geological history until 2004, making it one of the most recent additions to our understanding of Earth's timeline. The discovery of new fossils in locations like Canada, Australia, and Russia has only expanded our knowledge of this fleeting period. Yet, despite the growing fossil catalog, many unanswered questions remain. Were these organisms early offshoots of animals, or do they represent a lost experiment in life's history? And why did most of them disappear as abruptly as they arrived? The end of the Ediacaran period didn't occur in isolation. What marked its close was the onset of the Cambrian Explosion, a sudden burst of evolutionary activity that introduced mobile animals, predators, and much more aggressive ecosystems. The calm, steady world of the Ediacaran would be replaced by the dynamic chaos of survival and adaptation. Still, the Ediacaran period stands as a critical chapter in the story of life, where the first forays into multicellularity set the stage for the immense diversity to follow. Around 541 million years ago, something extraordinary began transforming life on Earth. This event, known as the Cambrian Explosion, marked a dramatic escalation in the complexity and diversity of organisms. Over the relatively short time of about 20 to 25 million years, fast on a geological scale, most of the major animal groups that exist today made their debut. For the first time, life on Earth was teeming with creatures that had specialized body structures, movement, and behavior, setting the stage for the ecosystems we recognize now. One of the key innovations of the Cambrian Explosion was the development of hard parts. Animals evolved shells, exoskeletons, and other protective coverings, which not only made them more resilient, but also led to vastly improved fossil preservation. This was crucial for scientists studying this epoch, as these durable structures left behind clear signatures in the fossil record. The advent of hard parts also marked the beginning of one of Earth's oldest struggles, the predator-prey dynamic. With predators developing ways to hunt and prey responding with protective armor or rapid movement, this arms race drove an evolutionary feedback loop of adaptation and counter-adaptation. Another defining feature of this period was the emergence of traits that formed the blueprint for modern animals. Early Cambrian creatures developed eyes for detecting predators, limbs for efficient movement across the sea floor, and centralized nervous systems that allowed more complex behaviors. These enhancements offered clear survival advantages in an increasingly competitive world. The appearance of complex body plans, including bilateral symmetry, segmented bodies, and specialized sensory organs, allowed organisms to exploit their environments in entirely new ways. For life on Earth, it represented a leap forward in both form and function. Among the standout creatures of this era was Anomalocaris. Considered one of the first apex predators, it roamed the oceans with grasping appendages to capture prey in a circular mouth lined with hardened plates. Another survivor in this fossil record, Opabinia, may have been alien-like in appearance, with a segmented body, 5 eyes, and a flexible claw-tipped proboscis extending from its head. Such bizarre adaptations speak to the period's experimental nature, where evolution branched out into forms that would later disappear entirely. Because the Cambrian Explosion unfolded underwater, its impact is immortalized in detailed fossil beds like the Burgess Shale in Canada and the Chengjiang Biota in China. These deposits preserved soft-bodied organisms so well that even their delicate tissues can still be studied. The creatures found in these sediments seem otherworldly by today's standards, providing glimpses into an era when evolutionary possibilities seemed boundless. From segmented worms to the precursors of arthropods, these fossil sites allow scientists a window into life's early diversity. One factor that made such rapid diversification possible was the increase in oxygen levels. Rising atmospheric oxygen provided the energy necessary to sustain more active metabolisms and behaviors, enabling life to move, hunt, and live in more complex ways. This small but critical environmental change fostered the explosion of biological complexity that defined the Cambrian. One of the most successful groups to emerge during this time was the trilobites. These hard-shelled arthropods, with their compound eyes and segmented bodies, dominated Earth's oceans for an astonishing 270 million years. While today they are long extinct, they existed over a period 1,000 times longer than humans have. Their endurance highlights how the traits developed during the Cambrian set some organisms up for long-term success. Although the term Cambrian Explosion might evoke images of an instant transformation, the changes occurred over millions of years. In evolutionary terms, however, it was a blink. This burst of innovation transformed life from a relatively uniform collection of soft-bodied creatures to a kaleidoscope of forms that resembled everything from insects to fish. The Cambrian Explosion wasn't just a boom of biodiversity, it was the blueprint stage for all animal life to come. The Ordovician period, spanning roughly 443 to 485 million years ago, was an age of extraordinary growth and diversification in Earth's oceans. After the evolutionary leaps of the Cambrian, marine life continued its upward trajectory, filling the seas with new and thriving species. Corals began constructing reefs, brachiopods anchored themselves to the sea floor in abundant numbers, and mollusks, particularly cephalopods, claimed dominance as some of the most formidable predators of the era. Trilobites, holdovers from the Cambrian, also maintained their prominent status, adapting to the rapidly evolving oceanic ecosystems. Among the newcomers to the evolutionary stage were the first vertebrates, jawless, armored fish, now categorized as ostracoderms. Though primitive by today's standards, these small, sluggish creatures marked a critical milestone in the lineage that would eventually lead to all vertebrate species, including us. Their bony exteriors offered protection and early adaptation to an increasingly competitive world. These fish were the humble beginnings of backboned animals, swimming through oceans alongside other strange and wonderful creatures of the time. Marine life during the Ordovician flourished in complex and interconnected ways. Underwater ecosystems became layered and structured, with intricate food webs forming as species filled specialized ecological roles. Reef-building organisms like early corals and algae transformed the sea floor into diverse underwater landscapes, supporting a boom in biodiversity. Much of this explosion in life can be connected to massive underwater volcanic activity. These eruptions enriched the oceans with key nutrients, fueling blooms of plankton, the foundation of the marine food chain. While the focus of this period is often on the teeming oceans, the Ordovician also saw the first tentative steps of life onto land. Fossil evidence points to the emergence of early plants, likely small liverwort-like mosses, along the shorelines. These hardy pioneers didn't yet have roots or vascular systems, but they made use of simple structures to survive in damp environments. Though modest in size and complexity, their arrival laid the groundwork for ecosystems that would one day stretch across the planet's surface. It was a quiet yet transformative step toward the terrestrial world we know today. But this era of abundance didn't last. The Ordovician period ended with the first of Earth's major mass extinctions, the Ordovician Silurian Extinction Event. Around 85% of marine species were wiped out, a dramatic collapse that reshaped life on Earth. The likely culprit of this catastrophe was a sudden, intense ice age. A significant drop in atmospheric carbon dioxide caused temperatures to fall, leading to the expansion of polar ice caps. As ice spread, global sea levels plummeted, drastically shrinking habitats for countless marine species. Those that couldn't adapt in time were lost to history. When the Ice Age eventually ended, the subsequent melting of glaciers created unstable conditions. Warming temperatures and rising sea levels led to further disruptions, preventing ecosystems from fully recovering until much later. This extinction event was so severe that it reset marine evolution, opening opportunities for entirely new species to rise in the following Silurian period. What survived this upheaval served as the foundation for the next wave of biodiversity, proving once again the resilience of life. During the Ordovician, cephalopods cemented their role as apex predators. Among them, giant nautiloids stood out for their size, with some growing over 6 meters long. These colossal hunters ruled the seas with precision. With their long conical shells and tentacle-like arms, they were the ancient equivalent of the great white shark, striking fear into smaller creatures. Their fossils remain striking evidence of just how dynamic and varied life had become during this period. The Ordovician period was a time of growth and exploration, transforming Earth into a haven for marine life and hinting at the first steps toward colonizing land. Yet nature's cycles remind us that no period of abundance is eternal. For all its progress, the Ordovician ended in a global trial that cleared the stage for evolution to begin anew. During the Silurian and Devonian periods, life made an astonishing leap. It moved out of the water and began colonizing land. This transition wasn't sudden or seamless. It was a slow and painstaking process that reshaped Earth's ecosystems forever. The first organisms to take this bold step weren't animals, but rather simple plants and fungi. These early plants were small and primitive, resembling modern mosses or liverworts. They spread across the damp shorelines, forming thin green mats that anchored themselves with rudimentary structures. Though fragile, their ability to stabilize soil and trap moisture marked the first steps toward transforming barren landscapes into life-supporting ecosystems. Fungi likely played a key role in this transition by forming symbiotic relationships with these early plants. They helped break down minerals in the rocky ground, making nutrients available and aiding plant growth. Together, these pioneers began to alter the atmosphere by drawing carbon dioxide out of the air. Fossil evidence suggests this gradual plant colonization may have triggered a cooling event, as CO2 levels fell and temperatures dropped slightly. These small, unnoticed changes would have profound effects on the planet's climate and the overall cycle of life. Arthropods were the first animals to follow plants onto land. Starting with millipede-like creatures and early scorpions, these terrestrial pioneers crept across primitive landscapes in search of food. Fossils from this era reveal small yet important adaptations, such as exoskeletons that retain moisture and limbs capable of movement on solid ground. By the late Silurian, arthropods were exploring thinly vegetated coastlines, and as plants became more established, some species began to thrive in these new patchy habitats. Fluctuating oxygen levels in the atmosphere likely helped these animals survive and evolve. Over time, their descendants would come to dominate terrestrial ecosystems in ways that remain visible today. The Devonian, often called the Age of Fishes, saw marine life reach unprecedented diversity. Oceans teemed with species ranging from tiny filter-feeding fish to terrifying predators like Dunkleosteus. This 10-meter-long armored fish had powerful jaws capable of slicing through prey in one swift motion, cementing its status as one of the first apex predators. Among the many fish species emerging during this time were jawed-fish and lobe-finned fish, the latter of which would play an especially monumental role. Lobe-finned fish developed robust, fleshly fins, supported by bony structures, giving them the strength to push themselves along the sea floor, or even onto land in shallow waters. These adaptations marked the beginnings of a lineage that would lead to tetrapods, four-limbed vertebrates capable of supporting their weight on land. One of the earliest examples of this evolutionary shift was Tiktaalik. Fossils of this remarkable creature reveal a fish with features that were part aquatic, part terrestrial. It had fins with strong wrist-like bones that allowed it to prop itself up, neck mobility for turning its head, and a flat crocodile-like skull. Though still tied to water, Tiktaalik was a transitional form, half fish, half amphibian, that bridged the gap between aquatic life and the first land-dwelling vertebrates. Meanwhile, plants on land were also undergoing significant transformations. Vascular plants evolved during the Devonian, developing internal systems for transporting water and nutrients. This advancement allowed plants to grow taller, expanding beyond low-lying mats to form the first forests. These ancient forests covered vast areas, with towering plants like lycophytes and ferns creating shade and changing the composition of the soil. Their growth released large quantities of oxygen into the atmosphere, reshaping the planet's air and preparing the way for more advanced terrestrial life. However, these ecosystems were far from stable, as land vegetation was still sparse and fragile, making them vulnerable to disruptions like flooding and wildfires. Through gradual but groundbreaking changes, life on Earth transitioned from watery depths to solid ground. Early land ecosystems may have been patchy and precarious, but they established the foundations of a terrestrial world. From the first swaying plants to the cautious steps of an arthropod or Tiktaalik, the Silurian and Devonian periods were a time of bold experimentation. As plants filled open spaces and animals adapted to breathe and move on land, Earth set the stage for a future where life would one day conquer every corner of its surface. Around 359 to 375 million years ago, the late Devonian extinction unfolded, leaving its mark as one of Earth's most prolonged ecological crises. Rather than a single catastrophic moment, it played out across millions of years through a series of environmental collapses that decimated around 75% of all species, particularly those living in the oceans. The rich marine ecosystems that had flourished during the Devonian were permanently reshaped. Reef-building organisms, once so abundant, suffered dramatic declines. The sprawling underwater coral reefs collapsed, taking countless species with them, including armored fish and many trilobites, groups that could no longer adapt to the shifting conditions. This extinction cascaded through Earth's ecosystems in waves rather than all at once. Scientists believe a combination of massive volcanic eruptions, oxygen-depleted oceans, a condition known as anoxia, and climate changes triggered by the rise of land plants were the main drivers. One of the most profound effects came from plants themselves. The earlier spread of land plants had already begun altering Earth's climate, and now that shift pushed ecosystems to the brink. This sudden drop in CO2 caused global temperatures to fall, tipping the planet toward a cooling trend. While this sounds like a relief for Earth's ecosystems, the cooling had devastating consequences underwater. Lower temperatures increased ocean stagnation, causing significant loss of oxygen and marine habitats, leading to toxic conditions that many species could not survive. The extinction's critical turning points include two well-known events, the Kellwasser Event and the Hindenburg Event. The Kellwasser Event was particularly destructive for coral reefs and deep-sea species. Warm, shallow waters transformed into inhospitable zones where life struggled to sustain itself. Later, the Hindenburg Event delivered what many consider the extinction's final blow, devastating what remained of marine ecosystems and ending the dominance of many once thriving groups. Together, these events acted like a prolonged chain reaction, steadily removing ecological stability while creating conditions too harsh for most species. Interestingly, the late Devonian may have cleared the way for some species to rise in the aftermath. Tetrapods, four-limbed vertebrates that had only begun to venture onto land, found themselves with opportunities as their marine competition dwindled. With fewer predators in an open landscape, early tetrapods started to diversify, setting the stage for their eventual dominance in terrestrial habitats. The extinction, though devastating, opened evolutionary niches for life forms to explore and adapt to radically altered environments. In addition to terrestrial factors, some researchers have speculated about possible extraterrestrial influences during this extinction period. A debated theory suggests that a gamma-ray burst, a violent cosmic explosion, might have played a partial role. A gamma-ray burst could have stripped away Earth's protective ozone layer, exposing life to harmful ultraviolet radiation. While evidence for this theory remains inconclusive, it serves as a reminder of how external forces could have amplified the effects of existing environmental stress. Despite the apparent loss of biodiversity, certain groups found ways to flourish during this bleak period. Fungi, for example, took full advantage of terrestrial ecosystems stripped of competition. One particularly fascinating example was prototaxites, a towering fungal structure resembling giant mushrooms that could grow up to 8 meters tall. These fungal giants likely dominated some early land environments, standing as strange remnants of persistence in a time of hardship. The late Devonian extinction, while a period of global collapse, wasn't solely a story of disappearance. It was also a turning point, one where the old ecosystems gave way to the beginnings of new ones. The slow and steady recovery that followed allowed life to continue adapting in surprising ways, ensuring Earth's evolutionary narrative was far from over. The Carboniferous period, spanning from 299 to 359 million years ago, ushered in one of the most unique eras in Earth's history. This time was defined by vast swamp-filled forests, dominated by towering lycopods, ferns, and horsetails. These plants stretched tens of meters high, forming dense, steamy canopies that covered much of the planet, particularly in the warm equatorial regions. The humid, oxygen-rich conditions of these swampy habitats made them ideal for plant growth, creating ecosystems unlike anything seen before or since. Over millions of years, these forests served as the source of the thick coal deposits we extract today, turning what was once ancient biomass into a major resource that powers modern technology. One of the defining characteristics of the Carboniferous atmosphere was its staggering oxygen level. At its peak, oxygen made up about 35% of the air, nearly 70% higher than the levels we breathe today. The abundance of oxygen profoundly shaped life during this period, particularly arthropods. With such a surplus, insects and other invertebrates were able to grow to extraordinary sizes. The most iconic example is Megafauna, a giant dragonfly-like insect sporting a wingspan of over 2.5 feet. These ancient flyers would have easily dwarfed modern birds and bats, their enormous wings cutting through the heavy forest air. On the ground, Arthroplura, a colossal millipede-like creature, slithered through the underbrush, growing up to 2.5 meters, approximately the length of a small car. These giants thrived in an environment where high oxygen levels allowed their smaller respiratory systems to support significantly larger bodies. Beyond the fantastical arthropods, the Carboniferous was also a pivotal time for vertebrates. Amphibians, which had begun exploring life on land during the Devonian, exploded in diversity. These creatures flourished in the water-soaked landscapes, with many growing far larger than their modern descendants. Some resembled crocodiles or salamanders in shape, living semi-aquatic lifestyles as they hunted for fish and smaller land animals. However, their reliance on moisture limited their ability to spread far from wetlands. It was during this period that evolution filled a gap, the appearance of amniotes. These were early vertebrates that developed a major innovation: eggs with protective shells. For the first time, animals could reproduce away from water, opening the door to life in drier habitats. This adaptation would pave the way for true reptiles, which would ultimately conquer harsh environments and become major players in the next geological chapters. The forests of the Carboniferous didn't only affect wildlife, they had profound impacts on the planet itself. As plants grew and decayed in endless cycles, they trapped massive amounts of carbon in their tissues and buried it within the accumulating layers of swamp sediment. This relentless carbon drawdown gradually reduced the amount of carbon dioxide in the atmosphere, contributing to significant cooling trends over time. By the late Carboniferous, Earth began to shift toward a colder and drier state, a transition that would challenge many species' ways of life. These changing climates hinted at the next chapter in Earth's story, where glaciers would advance, altering ecosystems once dominated by warm forests. The high oxygen content of the Carboniferous atmosphere would have been a double-edged sword for modern living organisms. For instance, simply breathing in this enriched air could have made you lightheaded due to the sheer amount of oxygen. It also made the environment uniquely flammable. Scientists speculate that wildfires during this time may have burned hotter and more frequently than they do today. With so much dense plant life to fuel the flames, fire likely played a recurring role in shaping these ancient forests. The long-gone darkness of those swampy forests is, in many ways, still with us today. The coal deposits formed from the undecayed plants of this time make modern energy consumption possible. Imagine the light bulb in your room or the steel in a building. Its story might trace back 300 million years to plants locked in ancient swamps. The Carboniferous wasn't just a time of giant insects and lush forests. It was a foundation for the planet we live on now, its legacy buried beneath our feet. The Permian period, stretching from 252 to 299 million years ago, marked a significant turning point in Earth's history. Unlike the swampy, humid landscapes of the Carboniferous that came before it, the Permian brought drier, more arid conditions. This shift in climate forced life to adapt in ways that would set the stage for future evolutionary success stories. The expansive swamps that had once dominated the planet gave way to drier ecosystems, characterized by vast deserts and sparse forests. These harsher environments became the proving grounds for a group of animals that could thrive away from water: reptiles. Reptiles had one critical advantage over their amphibian counterparts: their amniotic eggs. These eggs came with a hard or leathery shell, which protected the developing embryo and allowed it to survive in dry conditions. Unlike amphibians, which needed water to reproduce, reptiles were free to lay their eggs on land. This change freed them from the constant pull of aquatic environments and let them spread into terrain that had previously been inhospitable. With this new freedom, reptiles began diversifying quickly, filling ecological niches that amphibians could not. One standout group of Permian animals was the synapsids. Though technically reptile-like, synapsids weren't dinosaurs or even true reptiles. They occupied a unique branch of the evolutionary tree and would eventually give rise to mammals. Among the most famous synapsids was Dimetrodon, easily recognized by its dramatic sail-shaped back. This feature wasn't just for show. It likely helped regulate its body temperature, absorbing heat during cold mornings or releasing excess heat during hot days. Interestingly, despite its reptilian dinosaur-like appearance, Dimetrodon lived and died millions of years before any dinosaur walked the Earth. To put it in perspective, it's closer in time to modern humans than to a Tyrannosaurus rex. Meanwhile, the face of Earth's continents changed as well, merging into the supercontinent Pangaea. This vast landmass created extreme conditions. Coastal areas remained relatively lush, but the massive interior regions turned into deserts with intense temperature swings. These harsh conditions spurred further adaptations as animals and plants adjusted to the new environmental challenges. For example, early gymnosperms, plants like conifers, became dominant, replacing the dense Carboniferous forests. Unlike the swamp-dwelling plants of the past, gymnosperms thrived in drier climates, spreading across Pangaea's arid landscapes. In addition to Dimetrodon, the Permian hosted a variety of herbivorous megafauna, such as Edaphosaurus. With its bulky body and small head, this synapsid sported a sail similar to Dimetrodon's, though its purpose remains debated. Some scientists believe it may have served as a display to attract mates or intimidate rivals. Early therapsids, another subgroup of synapsids, also emerged during this time. These creatures were remarkable for showing traits we now associate with mammals. Some therapsids displayed evidence of semi-warm-blooded metabolisms, enabling them to regulate their internal temperature more effectively. Fossil evidence even suggests that certain therapsids may have had whiskers or fur-like coverings, offering an early hint of mammalian evolution tens of millions of years before true mammals arose. The Permian seas told a different story. Marine ecosystems were losing their dominance as the climate fluctuated. However, some incredible ocean predators still thrived, like enormous ammonites, whose spiral shells make them one of the most recognizable fossils today. Early sharks also roamed the oceans, taking advantage of the weakening marine biodiversity as other species struggled to survive. Life underwater faced challenges as Earth's shifting climate brought periods of instability. The Permian was a time of transformation for Earth's ecosystems. It was a period where plants, animals, and marine life were pushed to innovate or face extinction. Life on land became more adaptive, with reptiles rising to dominance through their evolutionary innovations. The stage was set for incredible developments in the millions of years to follow, but the challenges of the Permian were far from over. Around 252 million years ago, Earth plunged into its most catastrophic biological crisis, the Great Permian Extinction, better known as the Great Dying. This event was unparalleled, wiping out roughly 90 to 96% of all marine species and around 70% of terrestrial vertebrates. Entire ecosystems, from the deepest parts of the ocean to vast stretches of land, were obliterated. Life as it existed at the time was reshaped forever, leaving behind a scar in Earth's timeline that marked the end of the Permian period. The disaster likely began with the sequence of massive volcanic eruptions in what is now Siberia, forming the infamous Siberian traps. These eruptions unleashed staggering volumes of carbon dioxide, CO2, and methane into the atmosphere. The greenhouse effect spiraled out of control, causing global temperatures to soar. Some regions may have reached unlivable temperatures, with equatorial zones potentially exceeding 50 degrees Celsius, 122 degrees Fahrenheit. Global warming wasn't the only consequence. Oceans absorbed much of the CO2, becoming highly acidic. Rapid acidification destabilized marine ecosystems, especially for species reliant on calcium for their shells and skeletons. Coral reefs crumbled, ammonites dwindled, and many fish disappeared altogether. As if the oceans collapsing weren't enough, yet another deadly domino fell. Stagnant seas, depleted of oxygen, created perfect conditions for the buildup of hydrogen sulfide, an extremely toxic gas. This gas likely diffused into the atmosphere, poisoning air and water alike. Fossil evidence suggests that hydrogen sulfide emissions combined with already low oxygen levels to kill off most marine life, pushing species to extinction at an unprecedented rate. It wasn't just marine ecosystems that faced collapse. Land-dwelling vertebrates struggled to survive as food chains disintegrated. From the smallest insects to large herbivorous therapsids, survival became nearly impossible for most species. Despite the widespread loss, some organisms managed to endure in isolated pockets. Burrowing reptiles and certain early therapsids, like Lystrosaurus, were among the few survivors on land. Their ability to dig underground might have offered protection from the extreme temperatures and toxic air. These resilient animals, though few in number, formed the seeds of recovery in the aftermath of the extinction. Still, it would take millions of years for biodiversity to return to anything resembling its former levels. Recovery was exceptionally slow, with the balance and stability of ecosystems remaining fragile even as life began to adapt to the drastically altered conditions. Fungi seemed to thrive in the aftermath, uniquely suited to feed on the unprecedented amounts of plant and animal debris left behind. Fossil records show a spike in fungal activity, something scientists call the fungus spike. For a brief period, fungi played a dominant role in recycling organic material on Earth's surface. This resurgence painted a haunting picture, a world where decay reigned supreme, life desperately trying to reboot, while fungi thrived on the ashes of the past. The magnitude of the Great Dying was unparalleled, and its impacts reshaped the trajectory of life on Earth. Entire evolutionary lineages vanished, including many ancient trilobites and large synapsids. This left behind ecological openings that eventually allowed new groups, like the ancestors of dinosaurs, to rise and dominate in the Mesozoic era. The Extinction Event was a devastating reset, one that forced life to start over under entirely new rules, paving the way for the evolution of entirely different forms of dominance. The intensity of this event was a harsh reminder of Earth's volatility. With the atmosphere choked by CO2 and the oceans a toxic and hypoxic graveyard, life faced an existential crisis. What remained became a foundation for resilience, proving that life, no matter how damaged, has the capacity to recover. The Great Permian Extinction wasn't just an end, it also marked a brutal, violent beginning for the next chapter of Earth's story. The Triassic period, spanning 201 to 252 million years ago, was a monumental chapter in Earth's history, a time when life fought its way back from the devastation of the Great Permian Extinction. Ecosystems were barren and incomplete in the early years. So many ecological niches had been emptied that survival meant filling gaps left by the nearly 90% of species that went extinct. In this period of rebuilding, the stage was set for evolutionary experimentation. Reptiles proved to be the most opportunistic, rapidly diversifying in forms and lifestyles that would shape the planet's future. This was when the first true dinosaurs made their appearance. Early Triassic dinosaurs weren't the colossal creatures we often imagine, but rather small, nimble, and two-legged. Species like Eoraptor, barely a meter tall, could dart through the sparse conifer forests in search of food. Herrerasasaurus, although slightly larger at 3 to 4 meters long, was similarly built for agility and speed, rather than brute strength. These early dinosaurs were predators, likely hunting small reptiles and insects, or scavenging as necessary, all while competing with larger non-dinosaur reptiles. These light, fast, early forms wouldn't dominate during the Triassic, but they were laying the groundwork for a much larger story that would unfold in the Jurassic. Dinosaurs weren't the only notable vertebrates to emerge during this period. The first true mammals quietly entered the scene as well, evolving from small shrew-like therapsids that had managed to survive the Great Dying. These early mammals were incredibly unassuming tiny insect eaters, scurrying in the shadows of the burgeoning reptiles. They were nocturnal, an excellent strategy for avoiding the larger cold-blooded predators that ruled the daylight hours. This lifestyle also marked the beginning of some key mammalian adaptations, like better temperature regulation and improved sensory capabilities, which would set them up for later success. Earth itself was still recovering from massive upheavals, and its geography provided challenges that would shape life during the Triassic. The supercontinent Pangaea dominated the planet, stretching from pole to pole. This enormous landmass created extreme environments. The coastal edges experienced more moderate conditions, but central Pangaea was arid and harsh, ruled by vast deserts and intense seasonal swings. Life had to become tougher and more adaptable to deal with everything from searing heat to bone-chilling cold. It was in this context that drought-resistant plants like conifers began to flourish, covering the earth in scattered forests. These trees and the nutrient-poor vegetation became the primary food sources for herbivorous reptiles like Pleistocene, a bulky animal that reached up to 10 meters in length. In the oceans, life rebounded in its own dramatic way. Some reptiles returned to the seas, adapting once again to marine life. Ichthyosaurs were among the first of these marine reptiles and would evolve into giant streamlined predators within just a few million years. Shawnosaurus, one of the largest marine reptiles of the time, stood out as a true giant, eventually reaching school bus-like proportions. These creatures were a testament to how quickly evolution could scale life back up after catastrophic collapse. Yet, just as life was finding its footing, the story of the Triassic closed with another extinction event. This crisis, likely triggered by volcanic eruptions from the central Atlantic magmatic province, caused dramatic environmental shifts that wiped out many species and reshuffled ecosystems yet again. However, this extinction cleared the way for what would come next, the age of dinosaurs. It's fascinating to think that amidst all this change, mammals, though barely noticeable at the time, were a hidden success story, quietly surviving for over 200 million years. They stood the test of time before eventually becoming the dominant group, far outlasting the dinosaurs, whose reign was only just beginning. Life, once again, had proven its resilience, though another wave of challenges was always just around the corner. The Jurassic period, which spanned from 145 to 201 million years ago, marked a spectacular chapter in Earth's story, often referred to as the golden age of the dinosaurs. By now, the world had stabilized after the dramatic Triassic Extinction Event, and life was flourishing on land, in the seas, and in the skies. One of the most significant geological changes during this period was the gradual breakup of the supercontinent Pangaea. As Pangaea fractured into smaller landmasses, ocean currents shifted, and climates became wetter and more temperate. This gave rise to lush environments, dense conifer forests, and sprawling fern-filled plains, ideal backdrops for giant plant eaters to thrive. Dinosaurs took center stage during this era, creating ecosystems dominated by some of the largest creatures to ever walk the earth. Enormous herbivores like Brachiosaurus Diplodocus and Apatosaurus shaped their environment by their sheer size and appetites, eating vast amounts of vegetation as they moved through the ancient forests. These massive sauropods weren't just passive grazers. They played an active role in their ecosystems, creating pathways in the forest and even dispersing seeds through their diet. Brachiosaurus, uniquely adapted with its long neck angled upward, was a towering browser, snacking on high foliage that other herbivores couldn't reach. Of course, with massive prey came equally impressive predators. Allosaurus, one of the apex hunters of the Jurassic, ruled the land. This large theropod, with its sharp serrated teeth and powerful hind legs, likely hunted in small groups or as ambush predators, targeting young or weak members of sauropod herds. Fossil evidence of bite marks on bones suggests fierce battles between carnivores and their prey. And Allosaurus wasn't alone. Smaller theropods, possibly scavengers, worked the edges of these ecosystems, taking advantage of leftovers from larger kills. Meanwhile, the oceans were just as dynamic. Marine reptiles like pliosaurs and ichthyosaurs dominated the seas, their adaptations making them the undisputed rulers of the underwater world. Pliosaurs, with their broad paddle-shaped limbs and powerful jaws, were apex predators, capable of taking on anything they encountered. Some, like Liopleurodon, reached lengths rivaling modern whales, making them some of the most fearsome ocean predators in history. Ichthyosaurs, dolphin-like in their shape, were built for speed and agility, their streamlined bodies allowing them to pursue smaller fish and escape larger threats. These marine reptiles filled niches left empty after earlier extinctions and thrived in the warm Jurassic seas. The skies, too, saw remarkable innovations. Pterosaurs, the first flying reptiles, claimed the aerial realm with varying sizes and shapes. Some, like Rhamphorhynchus, were small and insectivorous, while others, such as Pterodactylus, had more elongated wings and may have hunted fish along coastlines. But soaring wasn't limited to pterosaurs. The lineage of dinosaurs itself was experimenting with flight, evidenced by creatures like Archaeopteryx. This feathered theropod combined the traits of dinosaurs and modern birds, with a mix of sharp claws, teeth, feathered wings, and a bony tail. Archaeopteryx represents a critical evolutionary step, showing how adaptations in the Jurassic were already laying the groundwork for birds. Even though the spotlight shone on dinosaurs, other creatures were quietly evolving underfoot. Mammals remained small, nocturnal, and elusive, avoiding attention from the ruling reptiles of the day. Despite their modest size, they were diversifying, with some even developing gliding capabilities, akin to modern flying squirrels. These adaptations allowed them to exploit new ecological niches, avoiding competition with the hulking reptiles. Over time, these early mammals would prove to be survivors, but during the Jurassic, they lived in relative obscurity. This period wasn't just about individual species thriving, it was about entire ecosystems becoming more cooperative and complex. Evidence of nesting behavior, herd movement, and predator-prey interactions suggests that Jurassic dinosaurs weren't solitary creatures, but often relied on group dynamics for survival. Fossilized trackways even give us glimpses into their daily lives, herds of sauropods moving together, potential stampedes, and even signs of swimming dinosaurs, their claws dragging along the riverbeds. The Jurassic was a time of giants, not just in size, but in the scale and complexity of life on Earth. Dinosaurs shaped the planet's ecosystems like never before, and modern birds were beginning their long evolutionary story. Overhead, pterosaurs swooped through humid skies, while massive marine reptiles patrolled the oceans. Though mammals watched quietly from the shadows, their moment had not yet come. For now, the world belonged to the dinosaurs. The Cretaceous period, lasting from 66 to 145 million years ago, was the grand finale of the dinosaurs' reign. It was a time of unparalleled biodiversity as ecosystems transformed and life pushed the boundaries of adaptation. Dinosaurs, which had already dominated for millions of years by this point, reached their peak in size, diversity, and ecological specialization. Iconic species like Tyrannosaurus rex ruled North America as apex predators, while Triceratops grazed its way across plains. Smaller but equally formidable dinosaurs like Velociraptor hunted in packs, relying on speed and intelligence to take down prey. Meanwhile, in different parts of the world, Spinosaurus, one of the largest carnivorous dinosaurs, stalked river systems, using its crocodile-like skull to catch fish. Although these giants defined the era, they were separated by both time and geography, thriving in ecosystems spread across the globe. One of the most remarkable developments of the Cretaceous was the emergence and spread of flowering plants, or angiosperms. Before this, most plants on Earth relied on spores or wind to reproduce, but flowering plants introduced a revolutionary relationship with pollinators. Brightly colored flowers and nutritious nectar attracted insects like early bees and beetles, while small birds began to play a role in dispersing seeds. This floral evolution reshaped ecosystems in profound ways. Entire habitats shifted as flowering plants flourished, supporting a wider diversity of herbivores. Dinosaurs, always quick to adapt, evolved alongside this change. Hadrosaurs, also known as duck-billed dinosaurs, developed incredibly advanced jaws and teeth. Their dental batteries, a set of hundreds, sometimes up to 1,000 teeth, allowed them to grind tough vegetation. These teeth continually replaced themselves, making them some of the most efficient herbivores of any time period. While dinosaurs ruled the land, the oceans were no less dramatic. Predators like Mosasaurus, a long-bodied reptile with razor-sharp teeth, were the undisputed titans of the seas. Reaching lengths of up to 17 meters, they hunted anything smaller than themselves, from fish to other marine reptiles. Elasmosaurus, with its absurdly long neck, specialized in scooping up fish and crustaceans in shallower waters. The Cretaceous oceans weren't just about survival, they were about dominance, with massive predators maintaining their grip on complex marine food chains. Above the surface, the skies became home to increasingly advanced flyers. While pterosaurs had already evolved in the Jurassic, the late Cretaceous saw some species, like Quetzalcoatlus, growing to unimaginable sizes, with wingspans rivaling small airplanes. At the same time, the lineage of modern birds began to emerge, descending from feathered theropod dinosaurs. This transition blurred the line between reptiles and birds, leaving behind fossils like Ichthyornis, which had a mix of modern bird-like wings and ancient features, such as teeth. Meanwhile, Earth itself went through tremendous geographical changes. The breakup of Pangaea continued, resulting in more distinct continents drifting toward their modern positions. This tectonic activity caused rising sea levels, flooding low-lying areas and creating vast inland seas in places like North America. Ecosystems became more isolated, leading to regional specialization. For example, the dinosaurs of North America, such as Ankylosaurus with its armored plates, differed from those in South America or Asia. Evolution on such a large and dynamic scale allowed dinosaurs to diversify throughout these regions, filling new ecological roles. Distinctions emerged between northern and southern landmasses, with unique faunas adapting to their specific climates and resources. This regionalization is one reason why fossils from the Cretaceous can look so different depending on where they're found, even within the same time frame. But perhaps the most surprising thing about this era is its proximity to us. While the infamous Stegosaurus lived much earlier, during the Jurassic, the timeline of Tyrannosaurus rex is closer to modern humans than to that heavily plated herbivore. The gap between T-Rex and us is around 65 million years, just a few million years less than the time separating it from its Jurassic relatives. It's a reminder of how brief humanity's history is on a geological scale. The Cretaceous period was a spectacle of life's ability to innovate and adapt, balancing on the edge of global change. In the end, the biodiversity and dominance of the dinosaurs couldn't save them from what would come next, the sudden and cataclysmic end of their era. Around 66 million years ago, Earth experienced one of the most catastrophic events in its history, bringing the Cretaceous period and the age of the dinosaurs to a sudden and violent end. An estimated 75% of all life on the planet was wiped out, including not just the non-avian dinosaurs but also countless marine species, flying reptiles, and plants. The primary cause of this mass extinction was a massive asteroid impact, a rock estimated to be 10 to 15 kilometers wide that struck what is now the Yucatan Peninsula in Mexico. Its landing left a scar we know today as the Chicxulub crater, a gaping structure more than 150 kilometers in diameter, buried beneath layers of sediment in the waters of the Gulf of Mexico. The impact itself unleashed energy equal to billions of nuclear bombs detonating simultaneously. In an instant, entire ecosystems near the point of collision were vaporized. The force created devastating shockwaves that triggered massive earthquakes and tsunamis, some of which carried walls of water hundreds of meters high far inland. Vast firestorms ignited as molten rock and debris rained down on forests and landscapes thousands of kilometers away, burning vast tracts of land. Anything in proximity to the impact zone stood no chance at survival, but the destruction didn't stop there. Its aftereffects rippled across the entire planet. The explosion ejected an immense amount of dust, soot, and aerosols into the atmosphere, which remained suspended for months, even years. The debris acted as a blanket, blocking out sunlight and plunging Earth into an extended period of darkness that resembled a nuclear winter. For plants cut off from sunlight, photosynthesis came to an abrupt halt. Without plants, food chains based on vegetation rapidly collapsed, starting with herbivores and cascading upward to carnivorous predators. Global temperatures dropped significantly, and ecosystems that had once thrived in tropical equable climates were thrown into chaos. Acid rain, caused by chemicals released by the impact, further poisoned the air, water, and soil, erasing already struggling species. Marine ecosystems weren't spared either. Ocean temperatures plummeted as the atmosphere cooled, while acidification from increased CO2 levels dealt a death blow to coral reefs and shell-forming organisms. Plankton, the foundation of the marine food web, suffered catastrophic losses, leading to the starvation of countless marine creatures. The combination of immediate destruction and lingering environmental fallout pushed the planet's biosphere to its limits. Remarkably, some life managed to survive. Burrowing mammals, capable of escaping the extreme surface temperatures by living underground, had a huge advantage. These small, adaptable creatures could endure long periods without sunlight, feeding on roots, insects, and carrion. Certain birds also survived, with their warm-blooded metabolisms and ability to adapt to shifting environmental conditions. Crocodilians, with their semi-aquatic lifestyles and relatively low energy requirements, came through largely unscathed. These survivors would go on to inherit an empty world, one that offered new opportunities for evolutionary expansion in the aftermath of the mass extinction. A fascinating detail about the asteroid impact is how precisely catastrophic its timing and location were. Some scientists believe that if the asteroid had struck almost anywhere else on the planet, like deep ocean areas or less volatile geological regions, the resulting environmental destruction might have been less severe. This idea raises the tantalizing scenario that under slightly different circumstances, dinosaurs might never have gone extinct, altering the course of evolution entirely. One lasting relic of this event can still be found scattered across the globe: tektites. These small glassy beads were formed when molten rock blasted into the air, cooled rapidly, and fell back to Earth. Traces of tektites have been discovered in sediment layers as far away as Asia and Australia, physical evidence of the unimaginable violence of the impact. Marking the KPG boundary, these tektites and other signs of global devastation serve as a stark reminder of the fragility of life in the face of cosmic forces. In the wake of the asteroid impact that ended the age of the dinosaurs, the world was a blank slate. With vast ecological niches left empty, mammals, small unassuming survivors of the KPG extinction, had their moment to rise. Within just a few million years, mammals began an evolutionary transformation that reshaped life on Earth. The survivors, many no longer than a rat, suddenly found themselves in a world where adaptability could spark rapid change. What began as tiny insect eaters scurrying around in the shadows of dinosaurs soon expanded into creatures of every size and lifestyle, occupying roles previously unthinkable. One of the major reasons mammals succeeded so quickly after the extinction event was their flexibility. They rapidly diversified into all sorts of forms, from arboreal climbers to burrowing specialists. Some, like the ancestors of modern hoofed animals, evolved herbivorous diets to take advantage of the flourishing plant life, while others grew into apex predators, capable of dominating their environments. Mammals were no longer shoved to the edges of ecosystems, they became the central players in them. Within an astonishingly short time, by evolutionary standards, some mammals went from being no bigger than mice to developing into beings the size of elephants, a leap that demonstrates the incredible pace of adaptation in this new world. During this period, mammals also split into three major groups that still dominate today: placentals, marsupials, and monotremes. Placental mammals, which make up the overwhelming majority of modern mammals, were particularly well adapted to thrive in diverse climates and ecosystems. Marsupials, though smaller in number, developed unique reproductive strategies, carrying their young in protective pouches. Monotremes, such as early egg-laying mammals, carried over traits from their ancient ancestry, while still filling their own ecological niches. These group distinctions allowed mammals to explore evolutionary strategies suited to continents that were drifting apart, creating increasingly isolated and unique habitats. Around this time, early primates began making their first appearance. These ancestors of humans were small tree-dwelling mammals that pushed the boundaries of adaptation in their environment. They evolved grasping hands suited for climbing, forward-facing eyes that provided binocular vision, and slightly larger brains to process the constant challenges of arboreal life. Though they lived an ordinary existence compared to today's humans, these traits were foundational steps toward intelligence and advanced behavior, ensuring that primates would one day play a significant evolutionary role. Earth's climate during this era was still warm and humid, a holdover from prehistoric times. This climate encouraged lush tropical rainforests, which became a hotbed of evolutionary action. Flowering plants co-evolved with mammals, alongside an explosion of insect species that mammals could feed on. This intricate relationship between plants, insects, and small mammals helped energize ecosystems in ways entirely new to Earth. Herbivores fed on the ever-expanding diversity of plant life, while trees provided shelter for creatures evolving into more specialized lifestyles. Meanwhile, some mammals became true giants. Paraceratherium, the towering relative of today's rhinoceros, was one of the largest terrestrial mammals to ever exist, stretching over 15 feet tall at the shoulder. On the other hand, species like Andrewsarchus, a wolf-like carnivore, reigned as dominant land predators, combining mammalian intelligence with raw physical power. Interestingly, evolution wasn't limited to the land. The oceans became a new frontier for mammals when some land-dwelling hoofed animals began returning to the sea. Over time, these creatures evolved into the first fully aquatic mammals, the ancestors of whales and dolphins. Adaptations like streamlined bodies, powerful tails, and the ability to surface for air transformed them into some of the most efficient marine predators. Curiously, the mammalian experiment with evolution led to an almost bizarre variety of forms. Some species grew quill-like spines as a defense mechanism, while others developed armored backs for protection. There were even mammals with gliding membranes to leap from tree to tree, a precursor to the kind of aerial adaptations seen in modern flying squirrels. Evolution in this era seemed to be operating on a principle of wild creativity, exploring countless possibilities as life rebounded and reshaped itself. Every adaptation was a bid for survival, and the mammals that succeeded were those able to seize the opportunities that nature presented. As the Paleogene and Neogene periods unfolded, between 2.6 and 66 million years ago, Earth began transforming into the world we recognize today. With ecosystems stabilizing, mammals played increasingly complex roles across land, sea, and air, shaping the planet's emerging biomes alongside birds and flowering plants. Forests became less chaotic and more defined, forming biomes like the boreal, temperate, and tropical forests that now blanket much of the Earth. These environments hosted intricate food webs with keystone species at their centers, large herbivores shaping plant growth and predators maintaining balance. As forests stabilized, grasslands also began to emerge, creating a whole new stage for evolution to play out. One of the most significant changes during this era was the rise of grasses. Around 30 to 40 million years ago, grass species radiated across the globe, altering landscapes at an unprecedented scale and sparking what could be called a grassy revolution. Unlike dense forests, grasslands offered wide open spaces, which reshaped how animals interacted with their environments. Grazing mammals like horses, antelope, and early elephants adapted to take advantage of this endlessly renewable food source. Fast-running limbs, specialized teeth, and herding behaviors became common traits among these animals, enabling them to thrive while avoiding predators. Grass didn't just transform plant-eating animals, it also influenced the predators that hunted them. Large carnivores like early cats and dogs evolved the speed and cunning needed to chase agile prey across open savannas, marking a shift in predator-prey dynamics that still persists today. Beyond reshaping animal behavior, grasses had an even larger impact on Earth itself. Unlike earlier plant systems, grass fundamentally altered the carbon cycle. Its complex root networks trapped carbon in the soil, which helped regulate atmospheric composition and contributed to global cooling. This interaction shaped Earth's climate and ecosystems, creating a feedback loop that reinforced the dominance of grasslands. What began as a quiet evolutionary success story quickly became a driving force behind planetary change. Meanwhile, the diversity of mammals and birds exploded, filling every ecological role across land, air, and sea. Cats refined their hunting prowess, becoming stealthy ambush predators. Dogs, meanwhile, evolved into cooperative hunters, forming packs to take down larger prey. Apes, including the ancestors of humans, adapted to both climbing and ground movement, developing dexterous hands and increasing intelligence. Songbirds emerged in incredible variety, filling the skies with the earliest forms of modern avian behavior, from long migrations to complex mating calls. In every part of the world, mammals and birds dominated their respective realms, pushing evolution to create some of the most specialized creatures Earth has ever seen. The oceans also went through a massive transformation. Ancient marine reptiles were replaced by modern predators like orcas, while whales continued their remarkable journey from land back to sea. Some, like the early whale Basilosaurus, still showed remnants of their terrestrial past, retaining tiny, useless hind limbs, a fascinating reminder of evolution's gradual work. Coral reefs, having rebounded from earlier extinctions, became major marine hubs, while new ecosystems like kelp forests developed along cooler coastlines, offering shelter to a diverse range of marine life. Geological upheavals added another layer of complexity to the formation of modern ecosystems. During this time, continental drift reshaped the globe, impacting climates and habitats. The formation of the Himalayas changed wind and weather patterns across Asia, while the closure of ancient seaways altered ocean currents, affecting marine ecosystems worldwide. The isolation of continents like Australia led to the emergence of some of the planet's most unique animals, such as marsupials and monotremes, which continued to evolve in relative isolation. At its core, this period wasn't just about animals and plants adapting. It was about the world itself taking on a recognizable form. Modern ecosystems did not simply appear. They were sculpted gradually through interconnected forces, from the rise of grasses to the shifting of tectonic plates. Today's Earth, with its savannas, forests, and reefs, is the product of millions of years of transformation, a mosaic of evolving life in an ever-changing planet. Every tree and blade of grass, every bird in the sky and predator on the plains, carries a story written during this time of monumental change. Around 2.6 million years ago, Earth entered the Quaternary period, a time defined by dramatic swings between glacial and interglacial phases, what we often call the Ice Age. These cycles weren't uniform or constant. Instead, they came in waves, with massive ice sheets advancing during glacial periods and retreating during warmer interglacial phases. Over the millions of years that followed, these shifts shaped the planet in ways that are still visible today. Gigantic glaciers carved valleys, ground mountains into plains, and left behind glacial lakes that remain part of modern landscapes. The driving force behind these repeated ice ages was a phenomenon called Milankovitch cycles. These cycles are small, predictable changes in Earth's orbit, tilt, and the wobble in its rotation. Over tens of thousands of years, these shifts altered how solar energy was distributed across the planet's surface. When less energy reached northern latitudes, global cooling occurred and glaciers spread. When orbital changes reversed the trend, the planet warmed again. While these orbital changes worked like a cosmic clock, their effects were amplified by feedback mechanisms. For example, as ice sheets expanded, they reflected more sunlight back into space, perpetuating the cooling. Carbon dioxide levels also dropped during these periods, further deepening the chill. Life during these times faced immense challenges. The immense weight of accumulated ice reshaped continents, advancing across what are now North America, Europe, and parts of Asia. These ice sheets could reach thicknesses of up to 3 kilometers, burying entire regions. Cities like Chicago, London, and Moscow, if they existed then, would have been swallowed under thousands of feet of ice. But between these icy pulses, warmer interglacial periods would emerge, providing small windows of relief for life to adapt and diversify. Animals that lived during these glaciations had to be remarkably resilient. Woolly mammoths roamed frozen tundras, using their thick fur and curved tusks for survival, while saber-toothed cats hunted the large herbivores that thrived in these cold conditions. Giant ground sloths also lumbered through the region, their massive size helping to retain heat in the freezing climate. The colder periods also had a significant effect on sea levels. During the height of glacial advances, water locked in ice sheets caused sea levels to drop by over 100 meters. This exposed vast stretches of land, including land bridges that connected continents. One notable example is Beringia, which linked Siberia to North America. This temporary landmass allowed animals, and eventually early humans, to migrate to new regions. These movements had far-reaching consequences as species expanded their ranges and ecosystems grew interconnected in ways that reshaped Earth's biodiversity. Meanwhile, tropical regions remained relatively stable, becoming climactic safe zones where countless species found refuge during colder periods. These areas served as biodiversity hotspots, preserving species that would later recolonize temperate zones during interglacial phases. In contrast, species in temperate zones had to constantly shift their ranges, moving southward when glaciers dominated and returning north during warmer periods. This repeated cycle of ecosystem collapse and recovery pushed evolutionary pressures to new extremes, creating some of the most specialized and well-adapted species of the time. Evidence from ice cores and sediment layers offers a fascinating glimpse into these ancient cycles. Ice cores drilled in Antarctica, for example, preserve trapped bubbles of atmosphere, letting scientists measure carbon dioxide concentrations and temperature changes over hundreds of thousands of years. These records not only reveal the details of past climate patterns, but also provide a roadmap to understanding future changes in Earth's climate. Even with the overwhelming challenges of the Ice Age, some species survived in the most improbable ways. The tardigrade, often called the immortal animal, endured these frigid cycles by entering a state of biological stasis. This microscopic creature was unaffected by the harsh environments that erased less adaptable species, proving that resilience sometimes comes in the smallest forms. At its peak, the Ice Age turned over 30% of Earth's surface into a frozen expanse. It sculpted the planet's continents and shaped the survival strategies of ancient life. Though often thought of as a harsh and unforgiving time, it was also a period of astounding resilience, driving both geological transformation and the ability of life to adapt amidst constant upheaval. The Pleistocene epoch was a world defined by extremes. Spanning from 11,700 to 2.6 million years ago, it was a time of relentless climate swings. Huge glaciers advanced and retreated across the continents, carving out valleys, gouging the landscape, and transforming ecosystems again and again. These shifting ice sheets weren't the only giants of this age, though. It was during the Pleistocene that Earth's land teemed with massive creatures, what we often call megafauna. Many of these animals seemed almost mythical in size and appearance. Mammoths with spiraling tusks and thick, shaggy coats roamed the tundras and icy plains, while saber-toothed cats, like the fearsome Smilodon, prowled the edges of herds in search of their next meal. Giant ground sloths, towering as tall as buildings when they reared up, slowly lumbered through ancient woodlands. And then there were the glyptodons, armored mammals as large as cars, covered in heavy domed shells, not unlike oversized turtles, a clear testament to evolution's creativity. At the same time, humans were taking their first faltering steps onto the evolutionary stage. The narrative of early humans is one of remarkable adaptability. From the tool-making Homo habilis to the endurance-hunting Homo erectus, and finally to Homo sapiens, our species emerged as a product of environmental challenges and innovation. While Megafauna relied on traits like long fur and thick layers of fat to handle the cold, humans approached the problem differently. They wore animal hides for warmth, crafted stone tools to carve meat or pierce bones, and discovered fire, a game changer that allowed cooking, protection, and the expansion into harsher climates. They didn't face the Ice Age alone, though. For much of this period, Homo sapiens shared their world with other human species, such as the robust Neanderthals in Europe and the elusive Denisovans in Asia. Evidence even suggests that interbreeding occurred, leaving traces of their DNA in modern populations. But adaptation wasn't the sole domain of humans. Megafauna, too, were shaped by icy landscapes and shifting climates. Mammoths developed hairier coats and grew closer in stature to their woolly cousins as the Ice Ages intensified. Woolly rhinos grazed on grassy tundras, their stocky bodies and robust horns well suited for digging beneath snow to find food during long winters. Many species evolved migration patterns, moving with the seasons to escape harsh conditions or find better resources. The ecosystems of this era pulsed with this constant give and take between ice and life, a delicate balance that could tip either way. Roughly 20,000 years ago, the last ice age reached its peak. Enormous glaciers blanketed North America, Europe, and parts of Asia, some towering nearly 2 miles thick. Sea levels dropped dramatically, exposing land bridges like Beringia, which connected Siberia to Alaska. These bridges, fleeting as they may have been, played an essential role during this time. They allowed the movement of animals like mammoths and bison into new territories, but also served as paths for human migration. It was around this time that Homo sapiens began spreading into the Americas and arriving in more remote parts of Eurasia and Australia. As the Earth warmed and the glaciers receded, the Pleistocene came to a quieter end, but not without significant losses. Many of the megafauna that had ruled the Ice Age suddenly vanished. The causes of their extinction remain one of the most riveting debates in science. Rapid climate change disrupted ecosystems, and as lush Ice Age grasslands gave way to forests and wetlands, many species struggled to adapt. At the same time, humans were becoming expert hunters. Armed with spears and coordinated social strategies, they sought out the largest creatures for food and resources. On continents like Australia and the Americas, where animals had little experience with human predators, extinction came swiftly. Megafauna deaths, coupled with warmer climates, marked the twilight of the Pleistocene giants. Still, the coexistence of humans and colossal ancestors like the short-faced bear or towering mammoths remains incredible. In some cases, early humans may have even created shelters out of mammoth bones, shaping their surroundings with ingenuity. The Ice Age wasn't just a test for survival. It was the beginning of humanity's rise as the planet's most resourceful species. Around 11,700 years ago, Earth emerged from the last major glaciation, ushering in the Holocene epoch. The relentless cycles of freezing and thawing that had dominated the Pleistocene retreated, giving way to a warmer, more stable climate. This period of relative consistency created fertile ground, both literally and figuratively, for the next great chapter in human history. Glaciers that had covered vast stretches of the northern hemisphere melted, sending billions of tons of water into the oceans. Sea levels rose drastically, drowning coastlines and submerging ancient land bridges like Beringia, which had once connected Siberia to Alaska. Entire landscapes transformed, isolating populations and redirecting migration routes. These geographic shifts set the stage for humans to begin settling in one place, rather than moving continuously. The melting ice also brought with it another transformation, an explosion in biodiversity. The vast cold plains that had sustained Ice Age megafauna gave way to warmer forests, rivers, and grasslands filled with wild plants and animals. Some of these, previously hunted for survival, began to serve a different purpose. People noticed that certain grasses, like wheat and barley, provided reliable nutrition. Others began harvesting rice along fertile riverbanks or cultivating maize in the Americas. Slowly, these wild plants were domesticated. Humans learned to select the hardiest and most productive varieties of crops, ensuring more consistent harvests. With this, agriculture was born. But it wasn't just plants that were domesticated. Animals that once roamed wild now played a more intimate role in human survival. Goats, sheep, pigs, and cows supplemented diets, provided raw materials like wool and leather, and became critical to early societies. Dogs, interestingly, may have been the first species humans domesticated, and long before agriculture even began. Evidence suggests humans formed partnerships with dogs over 15,000 years ago, using them for hunting, protection, and companionship. These bonds laid the foundation for the relationships between humans and animals we still see today. Stable food sources led to profound changes in human life. Freed from the constant pressure to hunt and gather, communities grew into permanent settlements. Food surpluses allowed populations to expand and created opportunities for specialized roles like toolmakers, builders, and leaders. In regions like the Fertile Crescent, favorable conditions led to the development of the earliest civilizations. Here, humans built some of history's first cities, and with them came trade, governance, and writing. Other centers of early civilization emerged independently in China, India, Mesoamerica, and Africa, where local plants and animals supported unique agricultural systems. For example, rice cultivation flourished in the Yangtze Valley in China, while maize became the cornerstone of Mesoamerican societies. The stability of the Holocene wasn't just reflected in human development. It became embedded in how humans planned and organized their lives. As people observed predictable seasons and weather patterns, they developed early calendars to track time for planting and harvesting. Irrigation systems brought water to crops in dry seasons, ensuring reliable food production even in more challenging climates. Societies began to study the stars, mapping celestial movements to better understand their environment, and creating early astronomy. These advances not only helped sustain growing populations, but also accelerated cultural achievements, from monumental architecture to complex spiritual practices. Speaking of monumental structures, one of the most intriguing examples from this era is Göbekli Tepe in modern-day Turkey. Built over 11,000 years ago, it predates agriculture, yet its towering stone pillars and carvings suggest a hunter-gatherer society capable of organizing significant labor for spiritual purposes. This site challenges the traditional narrative that farming came first, highlighting the intricate relationship between human belief systems and early community building. However, the rise of civilization came at a cost to the natural world. Permanent settlements and agriculture required land clearing on an unprecedented scale. Forests were cut down for timber and to make way for crops, while rivers were diverted to irrigate fields. Some animals once essential to these systems were hunted into extinction, further altering ecosystems. With time, humanity began reshaping the planet at a scale unmatched by any previous species. These early civilizations laid the foundations of the modern world in ways that still influence us today. From the domestication of wheat to the invention of the first writing systems, this pivotal period marked the dawn of humanity's transformation from nomads to creators of complex societies. Earth's history is a story of survival through chaos. Every extinction made way for something new, from tiny mammals in the dinosaur age to us. As we face our own challenges, what will the next chapter hold, and who will write it? Subscribe to explore the past and understand our future.